Right now, we are witnessing the greatest display of power humanity has ever achieved. The end of fossil fuels and the world's largest fusion reactor, ITER. Why are we here? Because this reactor has just defined the future of fusion energy. Fusion energy works just like the stars. It generates power by fusing atoms together. At 150 million degrees, hydrogen atoms become plasma due to extreme heat and are controlled by strong magnetic fields. In this state, atomic nuclei collide at incredible speeds, merge, and form helium atoms. This process converts matter directly into energy, releasing enormous amounts of heat. By mimicking the way the sun produces energy, this technology has the potential to create an unlimited, clean power source with minimal radioactive waste. This is exactly what ITER is aiming for. One of the hydrogen isotopes used, deuterium, exists abundantly in nature, meaning there is no resource shortage. The reactor is designed to operate continuously. Once activated, it could generate enough energy to last for a human lifetime. ITER is preparing to bring this revolutionary energy from the heart of Europe to the entire world. ITER means path in Latin, but it also stands for International Thermonuclear Experimental Reactor. Located in the Cataract region of France, this massive facility covers 180 hectares. It is the largest fusion reactor ever built and represents the peak of human technological achievement. And now, it has set a new goal, 2039, the future of fusion energy. The sole purpose of this international megaproject is to bring the power of the sun to Earth. To be realistic, humanity has never been this close to creating its own star. If successful, ITER could solve the global energy crisis forever and reshape the world's geopolitical balance. But there is also another possibility, the loss of billions of dollars. At first glance, this may seem like a project led by France or a demonstration of power by the European Union, but it is far more than that. Even countries that rarely agree on anything, the United States, China, Russia, South Korea, India, and Japan, are part of this initiative. ITER represents a rare example of global collaboration, shaping the future of energy. Only nations with the technological capacity and vision to invest in this field are involved in the project. The ITER project was first introduced in November 1985 during the Geneva Superpower Summit. Mikhail Gorbachev, General Secretary of the Soviet Union, proposed an international collaboration for the peaceful development of fusion energy to U.S. President Ronald Reagan. This historic step laid the foundation for what has now become one of the largest scientific projects in history. The ITER agreement was officially signed in Paris on November 21, 2006. After all member nations ratified the international treaty, the ITER organization was formally established on October 24, 2007. Following the agreement, the project's key objectives were determined. One of the major goals was to generate 500 megawatts of energy by 2025 while achieving a Q factor of 10, meaning that for every unit of energy input, ITER would produce 10 times more energy. In other words, with 50 megawatts of input power, the reactor aims to generate 500 megawatts of output power. To put that into perspective, 500 megawatts of energy is equivalent to 51,500 liters of gasoline. This power could light up all homes in Paris for an entire day, and it would take only 6 minutes to produce. Now, how much fuel is required for this? Just 1.57 grams of tritium. Yes, you heard that right. With only 1.5 grams of fuel, ITER can generate the same energy as 51,000 liters of gasoline, and it can do it in just 6 minutes. When you consider these facts, it becomes clear that fusion energy has the potential to eliminate fossil fuels entirely. First, you need a tokamak. A tokamak is a fusion reactor that confines plasma in a toroidal chamber using strong magnetic fields. It was first developed in 1958 in the Soviet Union, and its name comes from the Russian phrase. Physicists often refer to a tokamak as a donut, and for a good reason, it really does look like one. The ITER tokamak can confine 840 cubic meters of plasma. To put that into perspective, this volume is large enough to completely fill the interiors of 10 passenger buses. This means ITER will control and generate energy from a plasma the size of 10 buses. Heated to 150 million degrees Celsius, imagine a fireball at that temperature, floating in midair, held in place by nothing but magnetic fields. If these fields lose stability for even a fraction of a second, everything instantly vaporizes. This is why keeping the plasma stable for at least 6 minutes is absolutely critical. And to do this, ITER is using a gigantic machine weighing 23,000 tons. Yes, you heard that right. This massive structure, positioned at the very center of the reactor, measures 30 meters by 30 meters. To give you an idea of its size, it weighs 115 times more than an Antonov and Tu-25 cargo plane. The plasma chamber you see on the screen is where the plasma will flow. The walls of this chamber will be just 10 centimeters away from temperatures hotter than anything in our solar system. These walls must withstand 150 million degrees while being only 10 centimeters away. To achieve this, they are made of a special tungsten alloy that has already been developed, although further improvements are still ongoing. Additionally, these walls need to withstand the massive neutron bombardment produced by fusion and efficiently capture and transfer the enormous energy it generates. The plasma chamber and its walls weigh 5,000 tons, making them one of the most critical components of the entire system. Before the process begins, this chamber needs to be fully vacuum sealed, a task that is a technological challenge in itself, but is reported to be ready. Once the vacuum is achieved, the magnetic system surrounding the chamber is activated. At this stage, a tiny amount of fuel, hydrogen isotopes required for fusion, is injected into the system. Next, the solenoid, a giant electromagnetic coil that provides full magnetic control, is powered on. After this, the magic of physics begins. An electric field is generated inside the ring-shaped chamber, and the hydrogen gas, deuterium and tritium, starts moving in a circular motion within the tokamak. Then, the first heating system activates, injecting energy to turn the gas into plasma. As this happens, the entire system starts spinning rapidly. Following this, the primary heating system kicks in, and the journey to 150 million degrees begins. At this mind-blowing stage, atomic particles collide with each other, initiating the fusion process and transferring immense energy to the reactor walls. So how are these magnetic fields controlled? The system uses superconducting magnets, which must be maintained at minus 269 degrees Celsius to function properly. The superconducting magnets used in ITER's Tokamak reactor form the largest and most integrated superconducting magnetic system ever built. These magnets weigh a total of 10,000 tons, with a significant portion of that weight coming from the liquid helium used for cooling. To keep these superconducting magnets at minus 269 degrees Celsius, ITER requires 10,000 tons of liquid helium, which accounts for 1% of the world's annual liquid helium production. This massive magnetic system is responsible for initiating, confining, shaping, and controlling the plasma. Now, how far apart are these extreme temperatures? Just 2 meters. The insulation system used in ITER remains largely undisclosed, but managing such an extreme temperature difference is a true feat of engineering. When you examine the contributions of different countries to ITER, it becomes clear why a single nation could never build such a massive system alone. ITER's team consists of over 4,500 scientists and engineers, and within this workforce, 35 different languages are spoken. Creating a truly global project looks exactly like this. A scientific and technological collaboration of this scale is not just about producing limitless energy. It also holds huge strategic importance for world peace. If such a power source were controlled by a single country, it could shift the balance of global power dramatically. But by structuring ITER as a multinational collaboration, it ensures that energy is shared and that scientific advancements are distributed worldwide. Meanwhile, one of the core responsibilities of ITER's central software team is quantum computing compatibility. The world is changing rapidly, and quantum computers are expected to revolutionize material simulations and plasma movement predictions. To stay ahead, ITER is already developing fusion simulation systems that are compatible with quantum computing, preparing for the next generation of energy optimization. As for the current state of the project, ITER is not relying on a single reactor, but rather on multiple experimental reactors. For example, the West reactor in France focuses on material testing, while the JT-60SA reactor in Japan specializes in plasma processes. The data collected from these reactors directly guides ITER's Tokamak construction. These two supporting reactors have already achieved major breakthroughs. They set a record by maintaining stable plasma for 22 minutes and produced the largest plasma ever created. 160 cubic meters. These milestones are critical for ITER's success and future progress. Originally, 2025 was set as the year when ITER would begin producing positive energy. However, due to material issues in the superconducting magnets, this timeline has now been pushed to 2039. The real question is, how realistic is this new target? The best way to evaluate this is by looking at previous revisions. The 2025 goal was initially set in 2016, yet it was revised in 2024. In other words, as the original deadline approached, the planned timeline was extended by 14 years. Naturally, this raises doubts about whether future targets can be met. However, considering the advancements in superconducting technology over the past decade, even though the new timeline does not inspire full confidence, it is highly likely that positive fusion energy will be achieved by 2039. By 2039, we will see whether fusion energy becomes a reality. One thing is certain, ITER is one of the biggest scientific bets in history. Why? Because its current cost stands at 25 billion euros. If we look at what has been accomplished at the ITER site so far, we can see that the general structure of the Tokamak reactor has taken shape. By 2020, all construction work, including the closed assembly hall where the main Tokamak would be built, was completed. From this point, the focus shifted to technical construction, meaning the assembly of complex machinery. The first major milestone was in May 2020, when the 1,250-ton cryostat base, manufactured in India and transported by ship, was successfully lowered into the Tokamak assembly pit. This achievement was seen as the first major success. By October 2020, it was officially announced that the technical assembly of the Tokamak had begun. In 2021, the entire magnetic system of the Tokamak was assembled, a milestone regarded as a huge achievement. By 2022, work began on integrating the vacuum systems with the magnet systems, with each sector measuring 18 meters in height and weighing 1,380 tons. The first sector of the vacuum chamber was successfully assembled, which was expected to mark a turning point. In fact, completing this stage would have meant that the first full segment of the plasma chamber was ready. However, during a special helium leakage test, engineers discovered a micron-level defect in one of the vacuum vessel welds. This tiny flaw meant that everything had to be redone, leading to further delays and new revision dates. Currently, the defects need to be fixed, and the assembly process must be repeated. Despite these setbacks, a massive international fusion reactor is closer to becoming a reality than ever before. However, this does not mean energy production will begin immediately. A single defect in a magnet component can set the timeline back by 8 years. Yet, one undeniable fact remains. The world's most advanced nations continue to invest in this project, and their commitment makes halting this progress nearly impossible. See you in the next video.